Hi guys, Dr. Manis here in our second video in a series on gases. In this video, we're going to basically be looking at pressure, volume, temperature, and mole relationships. Okay, this is purely a qualitative idea for the fundamental properties of a gas. These relationships set up your gas laws. A lot of students blow off these relationships and just try to memorize the equations and such. But if you really have a good understanding of these, then the hard questions in the test, the explanation type questions, you can really understand. And basically, you can get a better grasp so you're not just mimicking your way through the course. So basically, we look at four properties. Every time we're going to be good little experimenters, okay? And we're going to say, hey, two things are going to be held constant, and basically they're ignored. And then the other two, one's going to be messed with, okay? And then the other one, we'll see how it goes, our independent, dependent variable type gig. Okay. And we're going to go through the works of four different scientists. First is Boyle, Robert Boyle. Okay. Boyle's law, he related P and V at constant temperature and number of moles. Okay. Basically a sample of a gas. And in this case, I'm basically going to be using this whole idea of a piston. Okay. I can sort of push down on this, like a plunger on a syringe. I can push down on that and change the volume, or pull back on it and change the volume. So basically, that's all I really want to do there. And if you notice, we have a volume of a gas, and it's going to be at a constant temperature and pressure, constant temperature in moles, and we're just going to mess with the volume and see what happens to the pressure. Okay. In this case, we go from a larger volume down to a smaller volume. If that space is decreased and the speed of the particles has not changed, odds are that as the volume has gone down, okay, the collisions with the walls, that pressure should be happening more frequently because they have a less space to traverse, okay, and going the same speed, and so the pressure should go up. Does that make sense? All right. This was Robert Boyle in 1662. As V1 to V2, the number of collisions increased in the same proportions that the volume decreased. Okay. If you do the math on these things, then any pressure, what basically he measured a bunch of pressures and volumes and realized that every time they were multiplied together, which is what you do for an inverse relationship, they always equal the exact same constant, and our constant is going to be a k. So basically, p times v is always equal to a k. Well, if p and v always equal k, then p1 v1 here should equal p2 v2. Because if a equals b and b equals c, then a should equal c. So these two things should equal each other, and that's how we come up with Boyle's law. p1 v1 equals p2 v2. Moving out of 1600s, we get to Gay-Lussac around 1800. Okay, Gay-Lussac did a bunch of stuff with gases. In this case, we're just relating pressure and temperature now, constant volume and number of moles. So for a plunger over here, okay, there's no extra gas in that plunger. We're going to lock the shaft of it in place, and we're going to increase the temperature. Okay, so the idea here is if we mess with the temperature, either increase or decrease the temperature, we mess with the temp, what's going to happen to the pressure? Okay, so if you increase the speed, okay, speed is increased, it stands to reason that the number of collisions is going to have to increase. Because if those puppies are moving faster, okay, then they're going to collide more frequently with the walls of the container. The volume hasn't changed. And that's the whole reason why you don't heat up a closed container. They tend to build up pressure. Okay, I still remember those stories. I won't go there. Anyway, you don't heat up a sealed container because things explode. Okay, so anyway, as temperature increased, pressure increased. This is Gay-Lussac from 1808. Temperature increases, pressure increases. That is basically a direct relationship. And for direct relationships, no matter how you scribble it like I do, pressure times you divide. For Robert Boyle, is an indirect relationship, so we multiply. But basically, if you look at Gay-Lussac, if you repeat his work and the work of Hamilton, okay, they take a lot of pressures, divide them by temperatures. The thing is, you always end up with a constant. Okay, if they're always the same gig again, P1 and T1 are equaling a constant, the second set's equaling the exact same number, so are the third, fourth, and fifth. In my lab with my high school kids, we measure like 5 different sets of them and say, hey, they're always equal to a constant. So yeah, P1, T1 will equal P2, T2. Again, if A equals B and B equals C, then A equals C. And this is Gay-Lussac's law. Okay, Charles' law. Charles' law was also investigated by Gay-Lussac, but he knew that Charles came first, so he credited Charles with it. Okay, first, and basically here we have volume and temperature at constant pressure and moles. Okay, so we go to our groovy little plunger that we got going on over there. Okay, if we heat it up and allow the volume to keep the pressure constant, then the volume will expand. Okay, is what we find out. If the gas is cooled, then the volume decreases. That's why, like, sometimes if you have something hot and you seal it up in a container, like your thermos or something like that, sometimes it can be really hard to get the cap off, things like that, because as the temperature changes, we affect volumes, pressures, all this sort of stuff. I'm digressing. But anyway, in this case, what we have here, if we cool, as we go from first set, as the temperature goes down, if we cool that puppy and drop it, like put a balloon in the freezer, okay, the volume's going to decrease, okay, because the pressure is staying constant. All right, as a football coach, I know like a lot of football coaches be like, the balls are losing air because the temperature's gotten colder out as it gone from summer into late fall. They didn't necessarily lose air so much as they got colder. Okay, so forget it, I'm digressing. Anyway, temperature goes down, the volume goes down. Again, we have a direct relationship here. And what Charles showed was that those two things are equal to a constant, just like Gay-Lussac. If they're always equal to a constant, okay, then you guessed it, they're going to be equal to each other. And this is Charles's law. The cool thing about Charles' law, that again, another digression, you can look at absolute zero this way. Volume can't be negative. Okay, so check out some temperatures, okay? Pretend you have a bunch of, you're in the lab, you measured a bunch of volumes, temperatures, you got a bunch of data points, and you plot those data points. So you put down, V1, T1, V2, T2, V3, V4, VT, and you plot that data, and you can make a line through that data, and that's fine. Usually don't go beyond your data set because it's not so valid, but let's interpolate that, let's expand that down. Okay, at some point, you're going to reach a finite little point of like, you can't get into a negative space. You can't get to negative volume. Okay, at that point, you've reached the coldest temperature that you can possibly get right here. Okay, and so you may have measured a first temperature, a second temperature, all these other temperatures, but no matter what they are, this puppy right here can't be less than negative 273 degrees C. Okay. That, we then say, okay, let's call that 0 and be Lord Kelvin and call that 0 Kelvin. Okay, and then step up from there. So minus 273, minus 272, we're going to call that 1 Kelvin. Minus 271 degrees C, we're going to call that 2 Kelvin, and so forth, till we get up to room temperature at 25 degrees C, and we call that 298 Kelvin. And so that's why we use Kelvin. It's an absolute scale because there aren't any negatives, but you can sort of see where it comes from. You can't have a negative volume, so that's why 0 Kelvin is the coldest you can get, and we just work our way up from there. Alrighty. Avogadro came a little bit later. He was a little not very well known. Decades later, they realized the importance of his work. But anyway, you can have a sample of gas. If you know anything about moles, that's Avogadro's number. So here we're dealing with volume and moles. That's what Avogadro did. He dealt with volumes and samples of gases and numbers of particles. Okay, so we're going to hold pressure and temperature constant and deal with volume and number of moles. Alrighty. If we increase the volume here as we go from the first to the second one, okay, to keep the pressure constant, the number of collisions constant at the same speed, we need to interject more particles. Because if the particles are going the same speed in a larger volume, the only way you're going to have more collisions with the walls and containers is if you have more particles. Okay, and so what Avogadro is showing us is that volume and the number of moles are going to be directly related. And as we saw through Charles's law and Gay-Lussac's law, direct relationships are division. Okay, So we go to Amadeo Avogadro and we say, hey, V over N is going to be equal to a constant. Okay, as we go from N1 to N2, V1 to V2, their V over N is going to be equal to a constant, and it's the same gig again. One set of data is equaling to the constant. The second set of data is equaling to the constant. So much like the other laws, we see something very similar in Avogadro's law. But what's special about Avogadro's law is we have number of moles changing, and we can relate that to a chemical equation because the coefficients are number of moles. So what I want you to see, look at Avogadro's law and cross multiply, rearrange that gig. So we got volume, ratio of volumes to ratio of moles. If you know, remember your stoichiometry, we have, conversion factors, you have mole to moles conversions. Okay, well, here's a mole to mole ratio. Okay, right here. Well, we're saying a mole to mole ratio, which is a coefficient ratio, and these problems, a mole to mole coefficient ratio is a volume ratio. So volume and can be coefficients. Well, that's kind of cool. Okay. So for example, say you have 2H2, oops, have this equation here, you have ratios, okay, 2H2 to 1O2 to 2 waters by moles, okay, but what you can say is the volume of water produced, okay, the volume of H2O produced is going to be not the sum of the H2 and the O2. So you can't say, hey, 2 liters of hydrogen gas added to 1 liter of oxygen gas doesn't make 3 liters of water. It makes 2 liters of water, okay, because we have a reaction going on. And volume ratio in reactions are mole ratios in reactions as long as temperature and pressure are kept constant. And that's kind of huge. Alrighty? But anyway, let's go back to all these ratios that we got going on. We had a bunch of them. We had V and T equaling K. We had P over T equaling K. Not to mention V and N equaling K with a division. And we had a groovy little multiplication. If we combine those guys into one gig, we end up with PV over NT equaling K. Okay? Well, changing K to R, I don't know why the gas constants are. Okay, but it is. PV over NT equals R. More commonly, it's written as PIV-NERT. I know, chuckle. But it's really easy to memorize if you just speak the words PIV-NERT. That is your ideal gas law. Okay? And the ideal gas law, we usually use it for one set of PV-NT data. I go over that in another video. All right. The gas constant is something you have to memorize. It's just a constant for any sets of gases. You got to memorize it. And it has some values. Okay, it really just depends upon the pressures. Most students memorize them because it's easier to memorize R values than to convert between all these various pressure units that are really commonly used. Okay, liters, moles, and Kelvin tend to be constant, but pressure units change a bunch depending upon really what you're doing in the lab. All right, so you just memorize those R values and use them. But what if you have two sets of data? Just like before, if A equals B and B equals C, da 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 da. If one equals R and the other set of data equals R, then lo and behold, the two sets of data equal to each other, and you combine the sets of data to be the combined gas law. Alrighty, it's really common to use the combined gas law when you have more than two sets of data. Okay, and the combined gas law, I have a lot of stuff written there. The advantage is, in the combined gas law, if something's held constant or something like that, you can go back and derive all those laws that we were just talking about. But anyway, we'll do that in some problems later on in another video. Right now, that was a mess of stuff thrown your way in these relationships, but you really should understand them so you can understand why the ideal and combined exist. Anyway, hope you learned something. I'm Dr. Manis. I'll talk to you later.